Welcome back. We continue with networking fundamentals. So let's continue with more definitions. A collection of computers, which we generally refer as nodes, and transmission channels, which we also refer to as links, that allow people to communicate over distances are actually referred to as network. And transmission channels actually allows the connectivity. Networks range in size from networks on chips to deep space networks. Connectivity is provided by a variety of transmission methods, which we'll be seeing them in detail in our following lectures. So we can divide the transmissions methods into two, wired transmission and wireless transmission. But actually we can also refer to them as guided and unguided, because in most of the wireless transmission, the data is actually transmitted over the air to almost all sites. So you cannot direct it to guide it directly to some place. So in most of the wired communication, this is possible because your wire is from point A to point B, so you guide your data from point A to point B. So in wired transmission, most famous methods are coaxial cable, twisted pair wiring, and fiber optics. In wireless transmissions, we have many methods: microwave line of sight, satellites, cellular systems, Hoc networks, and wireless sensor networks. That are the things that we are going to talk about. So let's start with wired transmission methods. The first one, we are going to talk about coaxial cable. This is typical in cable TV setups, operates as the transmission line since 1880. The first transatlantic coaxial cable in 1956, popular in networks in the 1980s. There are two wires, copper inner core and outer conductor, to reduce the interference from the wires in the environment. So approximate bandwidth capacity is 1 gigahertz. 1 bit per second requires a bandwidth between 1/14 hertz to 4 hertz. The exact amount depends on modulation. Modulation is used to match a digital stream to the spectrum carrying ability of the cable. Approximate carriage capacity is 8 gigabits per second. And it's used in mostly in broadband access to the internet, TV cable connection. And most frequently used type is RG6. So here we say it is like $1 per meter, but giving these numbers actually does not make much sense, because they become cheaper and cheaper every day. Even after we put these slides on the internet or the video, probably this would be $0.5 per meter. But anyway, so let's move on to the second part. That is the twisted pair cable. This is actually what we have used in the Ethernet cables. And actually this was initially, it was really slow. And people thought that this technology would fade away and people will use fiber optics cables. But it turned out that twisted pair cables are really useful and very cheap compared to other systems. So most of the time we use twisted pair cables in wired transmission methods. So these are lighter and thinner than coaxial cable. Two wires twisted together over their length. The twisted geometry reduces electromagnetic leakage, in other words, crosstalk, with nearby wires. So this allows long distances. We can even have several kilometers. It is, unshielded twisted pair since 1990s. There are many categories, as you can see here, but most of the time we use category 5 or 6, which allows actually gigabit Ethernet. So you can have 1 gigabit per second in category 6, but also in category 5. So some people think that category 5 doesn't allow you to have gigabit per second limit, but actually you can have. But of course, category 6, referred as Cat 6, by the way, provides you somewhat better connectivity. And in this case, category 8 is allows you to up to 40 gigabits per second, but this is designed only for data centers where distances between switches and servers are short, generally just a few meters. It is not intended for general office cabling, and also it would be not cheap to cover the whole building with that. So let's move on to fiber optic cables. These cables actually send light pulse, so you can send zeros and ones in this way. And the highest data carrying capacity of any wired medium is, I think, upper bounded by 50 terabits per second. This is silicon glass core that conducts lights. In 1970s, they were slow. In 1970s in a network, the problem was that computers were fast, so we had fast nodes, but slow communication links. So this was the main problem in the 1970s and also in the early days of the internet. With dial-up communication, you had 56 kilobits per second, which is really slow. And it is also an upper bound. Most of the time, you cannot achieve that speed anyway. But recently, what we have is that we have fast links and slow nodes, because now the transmission, connected communication links are really fast. So electronic bottleneck is the mismatch between fiber link speed and nodal electronics, for instance, server or computer speeds. The data rate has been much higher than the speed at which the standard electronics could load the fiber. And there are two types of fiber, single mode cable and multi-mode cable. And both of them have different properties and you have to choose depending on your needs. In the single mode cable, the capacity of a single channel ranges between 10 to 400 gigabits per second. Single mode has higher data rate potential. It preserves pulse shapes more accurately, and you can use it for long distances, more than, for instance, 80 kilometers or more. In the multi-mode cable, it has like 100 channels, and at least a channel has minimum capacity of 1 terabits per second. So a light pulse is divided into multiple spatial paths or modes, and time is different between the modes in reaching this receiver end. So this is how you distinguish the channels and the data. It is cheaper, but it can be used in short distances, for instance, distances less than 2 kilometers. So before moving on to wireless communication, we have to also think in the security of fiber optics cable. So most of the time it is assumed that it is really secure because we thought that it is hard to intercept the data when you send it through a fiber optic cable. But most of the time, as you can see here, the distances are short, for instance, 2 kilometers or 80 kilometers. So if you want to send data from here to United States, you also have to pass the ocean. So you cannot send data with these cables to that distances. So you have to increase the power of this data, let's say, from at some distances. So those places are good places to go inside and listen to the communication. So sometimes people say that these are secure communication, but we assume that people assume that you cannot listen to the communication here, but actually this is not true. Okay, so let's move on to wireless transmission methods. The first one, we are going to talk about microwave line of sight. In these transmissions, in the microwave frequencies, you can have 20 to 50 megabits per second. This is high frequency form of radio wave with short wavelengths, like 1 centimeter to 1 meter. It requires line of sight. This is really important. So the antenna, you are directing it to have to see the target. So they can be blocked by buildings, hills, and even the curvature of the earth. To overcome obstacles, microwave antennas are often placed on towers or hilltops. Also used in cellular phones and space communications, include satellite communications. So let's talk about transmission through satellites. Recently, there are more than 3,600 satellites in the orbit, and more than 1,000 are operational. To us, the most important ones are geostationary satellites. They orbit the Earth at a velocity to overcome the force of gravity. Orbital speed exactly matches the rotational speed of the Earth. So these satellites seem to hang over a fixed spot on Earth. So there is a specific distance from Earth's surface. It is, as written here, 35,786 kilometers. So at that point, the orbital speed exactly matches the rotational speed of the Earth. So they hang in the space at that point. So a typical geostationary satellite has several dozen transponders, relay amplifiers, each with a bandwidth of tens of megahertz. There are many different frequency bands. Here, some of the downlink and uplink gigahertz are listed. There are also low Earth orbit satellites and middle Earth orbit satellites. These are below the geostationary satellites, which were at the distance of 35,000 kilometers. So there was a LEOS attempt by Motorola's Iridium project for a global cell phone service in the 1990s, failed due to high service cost compared to local terrestrial cell phone services. So the idea was to send many satellites, and this way, I think after sending 70 or 80 satellites, their aim was to cover the whole Earth. So this way, regardless of which point on Earth you are, you will be able to reach to one of these satellites using a satellite phone or other suitable device. This way you could call from any place on Earth to another place on Earth. 6 orbits of 11 satellites each. Several satellites move across the sky over any location on Earth. Support for almost 250,000 conversations. Calls can be relayed from satellite to satellite. So this project died, failed due to the high cost, but it was replaced by Iridium Next project, which SpaceX actually performed. So this was the second generation worldwide network of telecommunication satellites. These are some of the dates where SpaceX launched their batch of Iridium Next satellites, and this project actually ended a few years ago when actually we were teaching this course. So this way, this project now concluded, and they actually cover the whole Earth now. So this way, you can have voice or data information coverage to satellite phones or pagers or integrated transceivers over the entire Earth's surface. As far as I know, these satellites will be operational until 2030, but I don't know what happens afterwards. Maybe they have to replace some of the satellites. So there are currently 82 operational satellites. I think 6 of them are spares, but 76 of them are active for service. So let's talk about challenges in transmission through satellites. There's a propagation delay, substantial time necessary for satellite message to travel. This delay makes satellite transmission unsuitable for timed communications protocols, for example, Ethernet. So second challenge is the security. Satellites cannot be aimed. Therefore, they broadcast their messages to an entire hemisphere. Anyone with the appropriate receiver can intercept the transmission. If necessary, if security is a concern, some sort of encryption must be employed. This is also kind of a valid concern for almost every wireless communication. So let's move on to transmission through cellular systems. Signals travel between a cell phone and a local base station antenna, which is hardwired into the public switch telephone network. A geographic region such as a city or suburb is divided into geographic subregions called cells. A base station at the center of each cell. The nearby base stations are wired into switching computer, the mobile switching center. that provides a path to the telephone network. When necessary, connectivity is changed from one base station to an adjacent one, namely handoff. So actually I want to make a few comments at this point. So as you can see, there is a base station, the one that is closest to you. Your mobile phone actually talks to it, then through a wired communication, it goes to the other mobile switching center and so on. So as you can see, there are change of medium when you call somebody from your mobile phone. And the link between you and the person, there's many different communication channels, first wireless, then wired, then again wireless, and so on. So at this point, when we want an end-to-end encryption, actually what we prefer is to our talk to be encrypted at our phone and reach to the person without change during all this process. But strangely, in our even in 4.5G, when you talk to somebody, okay, your communication is encrypted on your phone to the base station, but then base station decrypts it and sends to the switching server or the main server, hopefully again encrypting it in a different key or something, but we don't even know what happens there. So we are just assuming that there is an encryption during all of these processes. So it is important, especially for the GDPR and that kind of laws currently for the privacy. So I'm hoping that the 5G or in the future versions, we would have end-to-end encryption, which is very easy to deploy actually, but for some reason, it is not preferred so far. Second thing I wanted to mention is the handoff. So base stations has some coverage. So if you are mobile, you might be moving one station to other, so you might get close to another one. So in this case, the handoff occurs. So your communication is moved from one base station to the other one. But sometimes, if you are unlucky, you might be in the middle of two base stations. Maybe your home or your room is just in the middle of these intersections of the radius of these base stations. So even if you walk a few steps while you are talking in your room, you might change your base station, and sometimes these handoffs are not performed in a proper way, so your communication might be lost, or the person you're talking to might not hear you for a few seconds. So in that case, it is a good idea to stand still and don't move. Okay, let's move on to ad hoc networks. These are dynamic, decentralized, self-configuring networks, no pre-existing infrastructure, for example, no routers in managed wired ad hoc networks or no access points in managed wireless networks. Each node participates in routing by forwarding data for other nodes based on the dynamics of network connectivity and the routing algorithm in use. These are also known as multi-hop radio networks because in order to communicate with somebody, maybe there are 5 different nodes between you and that person, so you have to have multiple hops. This data is sent between all of these nodes to reach to the other person. There are many applications. Mobile ad hoc networks, also known as MANETs, are active research topics. Vehicular ad hoc networks, also called VANETs, are also active research topics. So in that scenario, vehicles and some roadside equipment communicate with each other. This way, you can send anonymous data saying that there is a traffic in this road or there is an accident in this road. So this way, you can suggest other people to use different routes. But of course, for this reason, you have to have a reason to participate, because using such a system might, drain your battery or something. So there are many different solutions or suggestions for this kind of networks. Another one is smartphone ad hoc networks. It employs smartphones to create peer-to-peer networks without relying on cellular carrier networks, wireless access points, or traditional network infrastructures. This is actually really important because especially in disasters like earthquakes and so on, there may be a problem with the infrastructure. Your internet might not work, but this kind of ad hoc solutions might help a lot of people. And nowadays it is really easy. Before on your mobile phones, but also on your laptops, it would be, you will take a lot of measures to take so that you can share the your internet connection or have a ad hoc network. But nowadays you can just by clicking a few buttons or saying that this is a mobile hotspot, you can create this kind of ad hoc networks. Other examples are Army and Navy tactical manets, Air Force UAV ad hoc networks, ad hoc home smart lighting to control lights over a smartphone or via computer. For example, Zigbee communication can be used. So these are very popular areas. Actually, this is what led to the idea of Internet of Things. So we will talk about it in a minute. But for this kind of small devices or short distance solutions, sometimes security is overlooked. So in the future, we might have real problems with some of the Internet of Things devices. So this is why we need some security standards for these devices. Otherwise, you will have situations like somebody turning turning the lights of your home and on again, but maybe they might be in different countries. So this kind of things actually happen and probably will happen more in the future. So let's talk about the security of ad hoc networks. Most wireless ad hoc networks do not implement any network access control. So they are vulnerable to resource consumption attacks, and malicious nodes might inject packets into the network for depleting the resources of the nodes relaying the packets. Even with authentication, these networks are vulnerable to packet dropping or delaying attacks. An intermediate node drops the packets or delays it rather than sending it to the next hop. So there might be malicious users. So it might be a good idea to have more than one node to send the data. But again, the geometry of the communication might change because these are mobile nodes. So sometimes communication might be dropped because of a single malicious node. Let's talk about wireless sensor networks, a group of special dispersed and dedicated sensors for monitoring and recording the physical conditions of the environment and organizing the collected data at a central location. Wireless sensor networks measure environmental conditions like temperature, sound, pollution levels, humidity, wind, and so on. And actually, there's no figure below, but I was hoping to put a picture here. As you can see, this is just a collection of nodes, but this time our nodes are not computers, but sensors. Each node is connected to a sensor. A typical wireless sensor unit has the following characteristics. It might be really small, a size from 1 millimeter to 1 centimeter. It might weigh less than 100 grams, cost less than $1. Data rate in the range of a few hundred bits per second to 100 kilobits per second. And power consumption is really small in these devices. For instance, as you can see, it's written here, it might be 1/10 of a Bluetooth transceiver in terms of power consumption. So these are also known as dust networks. So as you can see, these topics like wireless sensor networks and Internet of Things or WANs or ad hoc networks and so on are hard to distinguish. So it is hard to give a good definition to Internet of Things. So there's no such a good definition. So in the next slide, I will talk a little bit about how I see the Internet of Things, and we will talk about it in detail. So let's talk about wireless sensor networks as our last slide for that topic. Similar to wireless ad hoc networks in that they rely on wireless connectivity, spontaneous formation of networks so that sensor data can be transported wirelessly. In case of control of the sensors through bidirectional links, wireless sensor and actuator networks, in this case, they are referred to as this. So in the actuator scenario, the communication is bidirectional. So actuator might perform some operation on the data it receives and then might tell the sensors to act in a different way or perform some other operations. Sample application domains, any kind of monitoring application, for example, homes for climate control, biomedical applications such as glucose level monitoring beach pollution, etc., etc. So as you can see, wireless sensor networks are around for a very long time, and there is a lot of research on this topic. But now we move one step forward and we move on to the age of Internet of Things. So again, the definitions are not that clear for this kind of new topics, and it might be hard to see its difference from wireless sensor network. So I'm going to talk about how I see the situation in the case of Internet or Network of Things. NIST actually prefers the term Network of Things because your network doesn't have to be connected to the Internet. So this is a broader definition. So in terms of security, let's see how things happened and how we moved into this situation actually. So there was an evolutionary change in computing and information technologies. So years ago, there was a single computer and many users. So there was a big computer in the room. So a lot of people were using different keyboards or monitors so that they act like a terminal, but all of them were connected to the same computer. But with the invention of personal computers, we moved to an age of one computer, one user scenario. But nowadays, what we are seeing is that we have many computers and one user. So in this case, okay, a single person might have more than one desktop computers and more than one laptops, but we also have smartphones, tablets, smartwatch, and so on and so forth. When I say many computers, I'm actually referring to every device that has computational capacity and communication capacity. So this is how I see actually the Internet of Things. So many Internet of Things systems run on resource-constrained platforms, for example, mobile tokens without battery, RFIDs or medical implants that do not allow change of batteries. Since they do not allow change of batteries, they have to be secure, and you don't have to perform the surgery again and again to change the device and so on. Many IoT devices are extremely cost sensitive because they are deployed in extremely high volumes. For this reason, most of the time the security is overlooked, because this way you eliminate a lot of part of the chip, so it becomes cheaper. An industry needed lightweight cryptography for this kind of small devices for at least 20 years, even with the invention of smart cards and so on. But it became an active research area in academia over the last 10 years. Thus, industry deployed several proprietary self-made algorithms and many disasters happened. There were many examples for this kind of broken proprietary algorithms, like keylock, which actually allows you to open the door of your car or your garage door. My favorite classic were, I think, was most deployed contactless smart cards, and they were broken too. And there were many examples in this scenario. So this is why we are worried about the age of Internet of Things, because many solutions were broken before, and currently there isn't any standard for lightweight algorithms for these kind of devices. If your device have good computational power or memory and so on. For instance, when we say Internet of Things, people think about devices like Raspberry Pi, but Raspberry Pi is no different than a computer. They're really good in terms of computational power and memory. They have gigabytes of memory, and they have really good CPUs. So you can use any standards currently we are using, but in the Internet of Things, we are even seeing 4-bit microcontrollers and so on. So you should have security design for those devices too. This is why we currently need worldwide standards for these devices, or otherwise, if we are deploying a lot of IoT devices day by day, and in the future we might have some disasters. So this is why NIST currently is holding a lightweight crypto competition, assuming that when advanced encryption standard is not suitable for your device, they will suggest that then use this lightweight standard that we have chosen through a competition. And currently we are in the last stage of the competition. There are 10 algorithms are announced as finalists, and winner will be, or more than one winner will be announced in 2 years, I guess. So our next topic will be Network of Things, and we will look at it in the way NIST, how NIST sees that.